We have to pay attention to direction. Direction makes a big difference. That's why, by the way, Alec, you'll notice I've been writing my vector symbols so much more. I won't take marks off if you forget the vector symbol, but by writing the vector symbol, what I'm trying to remind myself subconsciously is, hey, make sure you pay attention to a left and a right, or an east and a west, or a north and a south, or an up and a down, or a rebounds off of a wall, or something like that. I'm going to have to let one way be positive and one way be negative. Okay. We've been talking about crumple zones a little bit. You might recall that I pummeled somebody with a Nerf baseball bat versus a ruler. And we said the reason that the Nerf baseball bat exhibited a smaller force was because time got bigger. And how the key to minimizing injury in a car accident is to increase the time of the collision. What will increasing the time do? What will it lower? How will it lower the acceleration? You're right. It's a kind of a two-step process. We had, what was the impulse equation that had time in it? Hopefully by now you'll have your green sheet in front of you, right? What was the impulse equation? Sorry? Okay, so by making time bigger, force gets smaller. And since F equals what? Either mass gets smaller or acceleration gets smaller. I don't think mass gets smaller, so acceleration gets smaller. Okay, so I agree. It will lower the acceleration. How does this work in those little smart cars? You know the ones I'm talking about. There's not much length there for a crumple zone. The engineers were very, very clever. They actually designed the engine itself to be the crumple zone. Put your pencils down, look up. Got it started at 5 minutes. Here's our smart car test.
James, 10 seconds.
We're going to smash it into a concrete barrier.
30, 5, give me space, waiting. 40,
Driving remotely.
5.
And we're going to hit it at 70 miles per hour. That's about 130 meters per second. Could you convert that to kilometers per hour, please? Sorry, 70 miles per hour. I did that totally backwards. That's about 35 meters, 40 meters per second. Probably 40 meters per second. Could you convert that to kilometers per hour, please? 40 times 3.6 is? It's right around 120K. Okay, so solid freeway speed. Do you see the engine crumple zone? See it?
From 70 miles an hour to naught in 1 second. The little smart hit with such energy that it moved 20 tons of concrete, leapt into the air and rebounded to the side of the road. We didn't know what we'd find when we reached the wreckage.
The steel cage has certainly done its job really well. You can still see the original shape, just that one nasty kink there. Don't forget this is a car without a roof. The plastic was just shattered. So without even the strength of the roof, there hasn't been that much effect. You can in fact open the door.
Would firefighters need the jaws of life to cut you out? Again, that right there is some pretty impressive engineering, because that would get you medical attention way faster, right? They're not having to cut you out. They can get you out and get you to an ambulance much faster.
Bits fly out. There's only really when you come around the front, you do see...
There's the engine designed as the crumple zone.
That massive
Yeah, what engine? Yeah,
impact.
it crumpled.
Around the other side, though, it still looks remarkably like a smart car. You can still full shape of the door. Indeed, the door not only...
Could you get the passenger out without the jaws of life? Again, that's some pretty good engineering.
Normally.
I wouldn't want to be in that. I'd still want a longer car if I could. But, you know, based on what they were dealt... Oh, the door even opens and shuts. Based on what they were stuck with, the engineers did a pretty good job using some good physics. Toilet paper physics. You can do physics anywhere, even in the bathroom. Have you ever noticed on those big, huge round rolls of toilet paper, the ones that they often have in commercial restrooms, if you tug on the toilet paper slowly, the round roll will turn, but if you yank on the toilet paper quickly, what will happen? How can the same thing break and not break? You've probably all taken it for granted. You probably all used that trick. How does that work? Put your pencils down, look up. So what we're going to have is a big wooden block. That's going to be our toilet roll simulator. And what I really mean by that is we're going to have a whole bunch of inertia, that which resists a force. The same way the big rolls of toilet paper, this is why it doesn't work when the rolls of toilet paper are mostly used up. You can't use that trick anymore. You need a lot of inertia, okay? And what we have is a tiny thread right here. This red rope is not part of the experiment. It's a safety line to keep everything from crashing down, so it's slack. But we do have a little black thread right there, and we have a second black thread right here. If we take that bottom thread and we yank it really quickly, will the bottom thread break or will the top thread break? The bottom thread right here. If we take this bottom thread right here and we're going to go 1, 2, yank it really quickly, where will it break? On the bottom or on the top? 3, 2, 1. What happened? Now, what if I do a steady pull increasing on that bottom string? Where will it break? On the top? Why? By the way, you've all actually instinctively noticed this growing up. You've taken advantage of that all over the place where you've realized, for example, if there's a big stack of magazines and you want the bottom one, do you pull it out slowly? No? What do you try and do? You've learned if I yank it out, the other ones might stay there, right? You noticed it with toilet paper, with the big toilet paper rolls. It's kind of what I did when I filled the jar with the plastic container with water and I did my version of the magician tablecloth trick. If I had pulled slowly, that jar is coming over the counter and spilling on somebody. We've taken advantage of it. What's going on there? We can explain it with impulse. So when we pull the string very quickly with a force greater than the maximum tension that it can support, the string will break, and the string will break right here because this has so much inertia, so much mass, and the time is so small that this will hardly experience any impulse. The impulse on the block is nearly zero since time is so much less than 1. Time is really tiny. When you use 2 less thans in math, that means really smaller than. Okay? And impulse is force times time. Such a small time, even though you're applying a big force, there's hardly any change in momentum on this block. It barely moves. The bottom string snaps. What about when we pull slowly? Okay. Oh, the top string does feel a force, but it's pretty negligible because there's such a small force there. We have basically tension still equals gravity. There's a tiny bit of extra pull force, but because the time is so small, because the impulse is so small, the force is so small. When we pull slowly, we can clearly transmit the force through the block to this string up here because time is so large. It's not an impulse situation anymore. Now it's just a straight force situation. And eventually we pull harder than the upper string. And the upper string has a bigger force than the smaller string, because the upper string is supporting the mass. The smaller string is not. The lower string is not. Let's actually get to today's lesson. We're going to look at collisions. We have two main types. First of all, objects can bounce off of each other after the collision. Curling rocks are good examples of that. They don't stick together. Billiard balls, if you're playing pool. Baseball and bat, I've never seen a baseball stick to the bat. Some car crashes, not all. If the objects bounce off of each other, we have a fancy word for that. We call it, here's the fancy physics word, and you will need to know this word. I will use this word on a test. Elastic. Whoop, elastic. An elastic collision is when the objects bounce off of each other. If the objects stick together after the collision, a football player tackling and holding on to the ball carrier as opposed to just body checking the ball carrier, a dart hitting a dartboard, assuming the dart sticks and because you don't suck at darts. Some car crashes, because some car crashes stick together. Ooh, a bullet that enters and lodges itself inside the target. We call these inelastic. How do I remember this, Mesa? Like students have been remembering it for 50 years. I think elastic, rubber band or rubber bounces apart. Inelastic, not elastic, doesn't bounce apart. So I always think, okay, which word am I going to use here? Elastic, rubber bounce apart. Inelastic doesn't bounce apart. Those are the two main types of collisions. Objects bounce apart or stick together. And I'll use that in my instructions. I'll say, oh, two cars collide inelastically. What I've just told you is they stuck together after the collision. You better take that into account. Collision examples. What do I have for collision examples, Mr. Dewick? I think it's here. Sure.
Elastic.
Oh, I gotta mute this. This is an elastic collision. They did not stick together. Ah, here we go. I had these numbered so you couldn't see from the title. So I've mixed these all up. This is the one I normally play. So this is an explosion. We'll look at these tomorrow. But here's your job. Can you figure out, are both these carts the same size, same mass? Or is one mass bigger than the other? What's the momentum right now, by the way? What will the momentum be after the explosion? 0. Okay, there's that one. There's this one.
Explosion.
And there's this one.
Big mass and small mass.
Oh, hang on, sorry. Just 2 for now. In one of these,
Unequal mass.
the masses are the same, and in one of these, the masses are different. So that's video 1.
Equal mass.
That's video 2.
Explosion.
Which one do you think the masses are different? Video 1 or video 2? Video 1?
Unequal mass.
Which mass is heavier, left one or right one? How can you tell? They both picked up the same momentum, and one's negative, one's positive. One had a bigger mass, must have a smaller velocity so that the momentums are the same magnitude. Okay. Now we're going to look at... Nope.
Elastic, big mass, and small.
3 collisions in a row. One is going to be 2 identical masses. One is going to be big hitting small. One is going to be small hitting big. See if you can figure out which is which.
Mass.
Okay, there's the first one. Let's watch it again.
Elastic, big mass, and small mass.
Here's the second one.
Elastic, small mass hits big mass.
Here's the third one.
Elastic.
First of all, those collisions, were they elastic or inelastic? Elastic. Okay. Back to the first one.
Elastic, big mass hits small mass.
Same size hitting same size, big hitting small, or small hitting big? Convince me.
Elastic, big mass hits small mass.
Okay. Basically, this one almost lost its momentum. Not quite. There was a little bit left. It transferred most of its momentum to the other cart, and the other cart took off faster than the first cart came in. That doesn't violate any laws. It picked up momentum. Smaller mass must have a bigger velocity. So I think this was big hitting small. I agree. What was that? Video 3. What about video 4?
Elastic, small mass hits
Small hitting big, or same size hitting same size? How do you know? In fact, it actually bounced back. It was so big, it actually bounced backwards, picking up some negative momentum, giving a bit more momentum to that big one, by the way. But that big one moved off with a much smaller velocity than the incoming one had coming in. So then you're saying this next one should be same hitting same?
elastic. Elastic.
If it was perfect, the first cart would come to a dead stop, giving all of its momentum to the second cart, which would take off at exactly the same velocity as the first cart came in. This is pretty close. There's friction and other things, but pretty close. Okay. We're now going to see 3 more collisions, and again, it's going to be same size hitting same size, big hitting small, small hitting big. See if you can figure out which one is which.
Elastic, big mass hits small mass.
Ooh, is that collision elastic or inelastic? Okay, inelastic. Let's watch it again.
Elastic, big mass hits small mass.
So they're going to stick together. It's that one.
In elastic, small mass hits big mass.
That one.
Inelastic.
One of those stood out. Which one looked most? Second one. What can we say about the second one here?
In elastic,
Small hitting big?
mass
Convince
hits
me.
big mass.
Okay. Momentum was still conserved, but mass got so much larger. What happens? Velocity has to get much smaller, so you have the same momentum. Yeah? Okay, let's look at the first one. If it's big hitting small, we shouldn't notice as much of a slowdown as the third one. Okay, there's that one.
Inelastic.
Big hitting small, they'll move off faster after the collision. I think the first one was big hitting small. It's tough to tell, and I think this one was, in fact, if they're both the same size, they should move off at half the velocity because the mass doubled. So the velocity should get half as big to keep momentum conserved. I like example 1. I like example 1. Example 1 is a nice question. A car traveling at 44 meters per second collides head-on with a car traveling 22 meters per second in the opposite direction. Everybody underline the phrase opposite direction. Why did I underline that phrase? What did I say we really had to pay attention to? I'm going to have to let one way be positive and one way be? Okay. Victor, do you want to let this 44 be positive or do you want to let this 44 be negative? Don't care, pick. Okay, I'm going to put a plus sign there. I'm going to put a big minus sign there so I don't forget. If the cars stick together, is this collision elastic or inelastic? I think at the bottom of the page, Let's do that, because that was one of the questions they wanted us to answer. What is the velocity of the wreckage immediately after the impact? Is this a collision? What are we going to use here? Conservation of momentum. The sum of all the momentum I start with equals the sum of all the momentum I finish with. Have I ever mentioned to you that I'm lazy but organized? I've said that once or twice. Luis, we're going to be lazy but organized. What do I mean? See that 1.5 times 10 to the 3? I want to call that mass A. Here's what I don't want to write. Mass A is 1.5. You know what? A. Anybody want to guess what I'm going to do next? Anybody want to guess what I'm going to do next? Please, people. B. If you do that, I'll figure it out. But I will say, please label them so that I know. You could have let the other one be A, but I will always label them in the order they give me in the word problem. That way, if you do that, that way all of our work will look the same if you're looking at one of my answer keys. You okay with that? Okay, so before the collision, what's moving? Mass A, mass B, or both? Read the question. Before the collision, what's moving? Mass A, mass B, or both? Stuck together or separate before the collision? Mass A, that's a subscript, VA initial, plus mass B, VB initial. Wham! They collide. After the collision, what's moving? Mass A, mass B, both or neither? How do you know it's both? Stuck together. In fact, I would have said both and stuck together. So it's going to look like this. Stuck together, mass A plus mass B. Stuck together, V final. What are we trying to find? Which one? There's 3. Ah! Oh! How will I get the VF by itself? What's the bracket doing to the VF? So? Am I lazy but organized? Yes? I'll figure out what you're getting. I think that's showing clear work. I think now we can plug in numbers. So this is the physics of if they're analyzing car crashes, like if the RCMP or something. It's more complicated. You have to take more like friction and road stuff into account in real life, but it starts here. What was mass A? I've scrolled down. You know what? That's 1500, which is less typing. I'm going to write it in non-scientific notation. What was velocity A initial? Was it 44? Which is pretty fast. That's about 130 kilometers an hour, right? Plus mass B was? Sorry? 1 times 10 to the 3, which is 1,000. Gabor, find what you're looking for and then finish, because that's the loudest bag I've ever heard. Go ahead, find it. You good? Okay. Okay. What was VB initial? No, it was not 22. How dare you? What? That's a silly mistake. Will I have that as an answer to pick from if this is a multiple choice question? Oh, yes. Divided by 1,500 plus 1,000. What do you get? Do this one in your head, Mr. Yeah, that ain't happening. 17.6 units. Did they give me a direction like east or west or north or south or anything like that? Okay. Well, I think then I'll just put a positive there based on what I let be positive, and I'll call that the direction. I don't have more information. If I gave this to you on a test, I would have had the word north or south or east or west for you to go with, okay? So, by the way, I'll turn the page, but I guess what happened is this. If my right hand on your left, if the tennis ball is car A and the brain is car B, they head-on, but car A won. They stuck together, and they kept going in the opposite direction, in the direction of car A. Does that make sense? Let's do another one. Curling stone is traveling due east. Okay. It strikes another curling stone that is moving east. Oh, how fast is the first curling stone moving? How fast is the second curling stone moving? This is getting rear-ended if you're in a car, but I used curling stones instead. So here's the physics of that. After the collision, the first stone is moving east at 0.6. I guess what happens, look up, the second stone is moving slow. First stone hits it, slows down. I think the second stone is going to speed up. I already think, just visualizing this, that my answer for the second stone is going to be bigger than 1.2. I see the word east. I don't see the word west, but just in case we should commit, let's let east be positive. Is there a collision?
Yes.
The sum of all the momentum that we start with equals the sum. How do I know this isn't an impulse question? They didn't say impulse, they didn't say force, and typically, if it's an impulse question and I'm asking you to find a final velocity, there usually will just be one object moving, not two. Am I lazy but organized? What am I going to do? What am I going to do?
So, the first one, I think.
Mr. Duick, what if they have the mass inside the paragraph and I can't get to it easy? Like if you have to, right? That's my lazy but organized. Before the collision, what's moving? Mass A, mass B, both or neither? Both? Stuck together or separate before the collision? So we're going to have mass A, V, A initial, mass B, V, B initial. Wham! They collide. After the collision, what's moving? Mass A, mass B, both or neither? Sorry for those of you who are listening to this with headphones on YouTube, but I'll bet you're awake now. Sorry, both stuck together or separate? Is this an elastic or an inelastic collision?
Yes.
So we're going to have mass A, V, A final, mass B, V, B final. And I made a little note here, east, positive, east, positive, east, positive. So these are the steps that you'll do before we actually dive on in. But now, what are we trying to find? What are we trying to find?
Yeah.
So let's see how good we are. Can we write an equation for that? Let's see. What side is the VB on? The right? So what's going to drop down like a domino? Then what? Minus this over, because the VB is not attached to it. Why minus? Because there's an invisible plus sign in front of it. Then what? Are we okay doing that in one step? If you can, I'd love to get you all there, because there's good nerd credit. Mummy, look what I did. I rewrote a big equation, but it's a nice time saver. And by the way, here's what we're saying. Here's all the momentum you started with. A kept some of it. The rest went into B. Okay, let's plug in the numbers. What was mass A? I've scrolled down. 18? VA initial? Nobody's answering. 2.6 plus 12.5 times 1.2 minus 18 times 0.65 all over 12.5. I was going to say I have no idea what the answer is. Well, as I visualize this, I think the answer is going to be bigger than 1.2, because I think if mass A slowed down, mass B must have sped up for momentum to be conserved. What do you get? Brackets around the top. You're all trying these on your calculator. It would be foolish not to, and then find that you can't get these right on the test. That would be the extreme silliness, right? Oh, VA, Mr. Dewick? Was I right? Is the answer bigger than 1.2? I hope. Okay. Kevin, what'd you get? 4.01. Anybody else? 4.01. Units, Kevin? Ooh, now I can give a direction. Direction. East. That's a terrible E. Or you can write the word east. A couple more, we're done. I think a couple more, we're done. One more and we're done. This is going to sound weird, but hopefully, Victor, you haven't learned a thing. This is just taking the pictures we looked at yesterday and saying this is what we'll have. Okay. 550 gram. Nice try, Mr. Dewick. How many kilograms? 0.55 kilograms. Oh, and you know what? A. 12 gram. Nice try, Mr. Dewick. 0.012 B. Now, if you don't have to use A and B, you could have used, for example, C for can and B for bullet. If you want to pick letters that make sense that way, go ahead as well. I'm fine with that. Oh, Paige, what word do you see right here? What word do you see right here? We need to let one way be positive and one way be... What do you want to let be positive? Probably east. So, positive, negative. Ooh, negative, right? I guess the soda is moving to the east at the same time as the bullet is traveling towards it. The bullet goes through, slows down. How fast will the soda be moving afterwards? This one I'm a little uncertain of. I'm pretty sure the soda is going to slow down. What I don't know is, did it completely change direction? Does it end up moving to the west as well? I don't know. Could happen. There's only one way to find out: conservation of momentum. The sum of all the momentum beforehand equals the sum of all the momentum after. Good yawn, Mesa? Now you're back. Mesa, before the collision, what's moving? Mass A, mass B, both, or neither? Stuck together or separate before the collision. So I'm going to have mass A, velocity A initial, plus mass B, velocity B initial. Wow, they collide. Wow, they collide! After the collision, what's moving Mesa? Mass A, mass B, both or neither? How do I know both? Definitely mass B. But what are they asking me to find? I think both. Stuck together or separate? Must be separate because if they were stuck together, I know the velocity of the can. It would be negative 55. So, mass A, VA, oh, not initial, Mr. Dewick. Final, mass B, VB, final. Conservation of momentum, Alex, I can't say that it's tough as much as mathematically. It's long. You got to do a fair bit of writing, but the equations, I'm going to argue, aren't too bad once you get them. Mesa, can you get, what are we trying to find, Mesa? V what? Which one? There's two VFs. VAF? Yes? Can you give me an equation for that? Can you do it in your head? Loud and proud. A little louder, please. Slow down. You're good. Yep, keep going. Oh, you folks have come such a long ways. Finish it off, Mesa. What was mass A? 0.55. Velocity A? Sorry? Mass B was at 0.015? 12. Wolf, you're good? Okay. Looked like you're having a challenge. You're good? Keep going. Velocity of B initial? Sorry? Sorry? What? How do you know? Did we not put a negative in front of it? If you didn't, you should have, right? Do your negatives and positives before you dive on in, because you can see how easy it is to oops along the way. Negative 250. Minus 0.012. What was the final velocity of object B, folks? Negative 55. All over mass A. I have no idea what the answer is. I don't know whether this can ends up going west after the collision or slowing down going east. I do know it's going to slow down. It's going to be less than 25 east. But I have no idea otherwise. Odetta, what'd you get? 0.7? Anybody else? Positive 0.7 or negative 0.7?
Positive.
Direction? So this, you know what? The can, is it 0.7? I need some, yes? 0.7? So, I'm sorry, I'm mishearing. 20.7. Thank you. I was going, that seemed so small. That's why I kept asking. Okay, I did a little math in my 20.7. Is that right? Round it off properly? Meters per second. Direction, Odetta? So how fast was the can going originally? 25? How fast after? 20.7. It slowed down not by much. How come? The bullet didn't have much mass. Even though it had a lot of velocity, it didn't impart much of its momentum to the can. And the can had enough mass that even though when it absorbed the momentum, it didn't change its velocity much. You can kind of start to visualize these a little bit as you get good. Oh, elastic or inelastic?
Elastic.
Did they stick together? Okay. In fact, they went through each other. What's your homework? Number one, I only see one object. This is not a conservation of momentum question. This is an impulse question, I'll bet you, because I don't see a second mass in the question. Oh yeah, what's the linear moment, final momentum, impulse, blah, 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 blah. Ooh, number 2 is a collision. This is a job for conservation of momentum. 3 is good. 4 is good. 5 is good. 6 is good. 7 is good. Mr. Duke, why didn't you just say all of them? Because I like messing with you. Okay. We're basically done the unit. Tomorrow when we look at explosions, you know what the spoiler alert is? Before the bomb goes off, what's its momentum? Be obvious. After the bomb goes off then, what's its momentum? Be obvious. They'll just be in opposite directions. We can, with physics right now, you can only look at 2 pieces flying apart. If you ask me, I can show you how you can do 3 or 4 pieces flying at angles. It just takes some trig.